Hello friends, welcome to IFAS. Hopefully you would be enjoying the classes and I'm very hopeful that you would be developing your concepts. Okay, so again I am saying try to make the concepts, try to understand the things, make short notes, try to solve the questions from different examinations, especially from the topics what we are learning. Okay, so my dear friends, the topic for today is carbohydrates. So we are talking about biomolecules, and among the biomolecules, the first molecule we are discussing is which is most abundant on earth, and that is carbohydrate. So what are carbohydrates? As the name suggests, carbohydrates are the hydrated form of carbon. They are hydrated form of carbon. What this means to us, that let's say we write it as this is a carbon, this is water. So in other words, water is interacting with a carbon. And that's why we can say that the general formula for the carbohydrate is CnH2nOn. That is, carbon, hydrogen and oxygen, they occur in molar ratio of 1:2:1. That is, if you try to find out the molar ratio of carbon, hydrogen, oxygen, it will be 1:2:1. And that hold it true for a simple carbohydrates. So they are the hydrated form of carbon. Their general formula is CnH2nOn. Further, these carbohydrates, my dear friend, they, from chemistry point of view, they are polyhydroxy. They are, from chemistry point of view, they are polyhydroxy aldehydes or ketones. Means they have either CHO group, that is referred to as aldehyde, or they have C double bond O group, which is referred to as ketone. But they are not simple aldehyde or they are not simple ketone. One more condition has to be fulfilled, that is the presence of more than one OH group. They should be there. So polyhydroxy, either aldehyde or ketone, they are referred to as carbohydrates. Carbohydrates, my dear friend, they are most abundant biomolecule. They are most abundant biomolecule on earth. Carbohydrates, if we broadly talk, they play both functional, they have both functional and the structural role. That is, they may provide an energy which is utilized for the functioning of cell or organism. They may be the component of cell wall, that is making a structural component. So this is, friends, the introduction to carbohydrates. Carbohydrates, they may be broadly divided into two classes. There are two main classes of carbohydrates. This could be monosaccharides, or these could be polysaccharides. Polysaccharides, these may be small or they may be large. Now, monosaccharides, for which we will talk in much detail, these are simple sugars. While polysaccharides, they are having two or more sugars linked by a bond referred to as, the bond which is present in the sugar, the bond is referred to as glycosidic. Basically, from chemistry point of view, this bond is a ether bond. If polysaccharides, they are small, that is having a 2 to 20 sugar residue, then such polysaccharides are often referred to as oligosaccharides. That is some book. They classify the carbohydrates three categories: monosaccharides, oligosaccharides and polysaccharides. We are saying that the oligosaccharides, these are the small polysaccharides. Okay, are you getting this? Okay, so this is the two major classes of the carbohydrates are monosaccharides and polysaccharides, and the bond which is present in the polysaccharide is referred to as glycosidic bond. Let's move further. Monosaccharides. Monosaccharides, these are the simplest sugar that is they cannot be further hydrolyzed. They cannot be further hydrolyzed into sugars. They themselves are the basic sugars. If you hydrolyze, you will not get a sugar. These are the smallest sugar which are known. These monosaccharides, these are repeating, or we can say monomeric units in polysaccharides. That if you carry out a complete hydrolysis of polysaccharides, you will get these monosaccharides. These monosaccharides will later on see that why this is so, but all monosaccharides, these are reducing sugar because they have free aldehyde or ketone group. Why they reducing sugar? Because they have free aldehyde or ketone sugar or group in a sugar. This may not be hold true for polysaccharides. Polysaccharides may be reducing, may be non-reducing, but all monosaccharides, since they are not participating in the glycosidic bond formation, they all are reducing sugar. Now, monosaccharides, depending upon the number of carbon, further they may be divided into triose, tetrose, and so on. The smallest sugar which can technically be classified as carbohydrate is 3 carbon, because for at least 2 carbon you need OH group, and for 1 carbon or at 1 carbon you need an aldehyde group. So the simplest carbohydrate which is possible is triose. So monosaccharides, if they are of 3 carbon, they are referred to as triose. If they are of 4 carbon, they are referred to as tetrose. If they are of 5 carbon, they are referred to as pentose. If they are of 6 carbon, they are referred to as hexose. If monosaccharides, they are of 7 carbon, they are referred to as heptose, and so on. The most common monosaccharide in biological system is hexose. And you can also find these triose, tetrose, pentose, heptose as metabolic intermediates, that is as an intermediate in glycolysis, in an HMP pathway, and various other metabolic pathway like gluconeogenesis. Now the simplest sugar is monosaccharide, and within a monosaccharide the simplest sugar is the triose, which is composed of 3 carbon. So this is the structure of triose, where there are 3 carbon. This is carbon 1, this is carbon 2, this is carbon 3. This 3 carbon is referred to as, since it is an aldehydic form, this is referred to as glyceraldehyde. And here we are representing 2 different forms of glyceraldehyde, that is, this is the glyceraldehyde, then this is a mirror image of this glyceraldehyde, where OH group here it is on the left side, this OH group is on right side on the chiral carbon. If OH group is on left side, this is referred to as L form of glyceraldehyde. If OH group is on right side, is referred to as D form of glyceraldehyde. So on basis of orientation of OH group at chiral carbon. Chiral carbon is a carbon where all functional groups are different. So this is the chiral carbon because you are having OH one side, H another side, CH2OH another side, CHO another side. So on basis of orientation of OH group at a chiral carbon, 2 enantiomeric forms are possible. Enantiomeric forms we will study, that is, these are mirror images, that is D form if the OH group is on right side, and L form if OH group is on left side. So the simplest monosaccharide is triose, composed of 3 carbon. The aldehydic version is glyceraldehyde. Glyceraldehyde, it has 1 chiral carbon. The ketonic version of triose is, so this is 3 carbon, and obviously aldehyde group it resides at first place. The ketone group cannot be at first place. This is now at second place. Whether it is an aldehyde group or whether it is a ketone group, one thing which is common in both is C double bond O, that is referred to as carbonyl group. Carbonyl group is present in ketone, carbonyl group is also present in aldehyde. But the ketones, they are often at functional group is at second position, while aldehyde, the functional group would be at first position. So this is OH group on first position, OH group is on third position, so that polyhydroxy condition could be satisfied. Now this is a triose, that is referred to as dihydroxy acetone. My dear friends, this dihydroxy acetone, it is the only carbohydrate which lack chiral carbon. So for dihydroxy acetone there would be no mirror images, there would be no enantiomers, means you cannot use the term D or L for dihydroxy acetone. Nor this will show any kind of optical activity because it is lacking a chiral carbon. So if once it is lacking a chiral carbon, the optical activity is not possible. Okay, so let's move further. Tetrose. The example of aldehydic tetrose is erythrose and triose. Again, you do not have to remember these structures. Here I have drawn the structure simply to highlight the differences between the erythrose and triose or erythrulose. For example, in erythrose, again there could be 2 forms, D erythrose and L erythrose. In the D erythrose, both the OH group on chiral carbon, because now there are 2 chiral carbon, both the OH group on chiral carbon is on the right side, while in L form both these OH group, they are on the left side. While in case of triose, what you find is that OH group which is present on second carbon is on the left side, while on third carbon it is right side in a D form of triose. If it is a L form triose, the things will be reverse. It would be simply a mirror image of this. Erythrose is an aldehydic sugar. Erythrulose is a ketonic sugar, where instead of aldehydic group, here you are having a ketone group. That's the only difference. But since ketone group is on second place, one chiral carbon has been compromised. That is, erythrose, it was having a 2 chiral carbon. There were 2 chiral carbon in erythrose or triose. That is carbon 2 and carbon 3. But the ketonic version, 1 chiral carbon is lesser. Why? Because at second place, now there is a ketone group. So they have only 1 chiral carbon. That is a carbon 3. So the structure which is drawn is L form of erythrose and D form of erythrose. Again, the structure is not important. Similarly, the important forms of pentose include, again, structure is not important. You have to keep the name of you have to remember the names. The important aldehydic version of the pentoses are D-ribose, D-arabinose, D-xylose and D-lactose. If you are interested in the structure, then you find that in D-ribose all the OH group is on right side. While in arabose, this is carbon 1, this is carbon 2, carbon 3, carbon 4, carbon 5. In arabinose, the OH group at carbon 2 moves to left side. In xylose, the OH group at carbon 3 moves to the left side. In lactose, carbon 2 and carbon 3 both moves to the left side in comparison to D-ribose. Again, we do not have to remember the structures. Similarly, there are ketonic version referred to as D-ribulose and D-xylulose. From xylose you will get xylulose, from ribose you will get ribulose. Generally, for an aldehydic sugar, the suffix which is utilized is OSE. For ketonic sugar, the suffix which is utilized often is ULOSE. So you must able to differentiate what you mean by ribose and what you mean by ribulose. Okay, ribulose is a ketonic sugar, ribose is an aldehydic sugar. You can see that in these aldehydic pentose forms, there are now 3 chiral carbons. That is carbon number 2, carbon number 3 and carbon number 4. In ketonic versions, this carbon second cannot be chiral. So in ketones, what you find is there are now only 2 chiral carbon. That is carbon 3 and carbon 4. That is ketonic version of sugar. They are having 1 lesser chiral carbon as compared to an aldehydic sugar. So glyceraldehyde, which is triose, was having 1 chiral carbon. Then dihydroxyacetone, which is also a triose but a ketonic version, was having a 0 chiral carbon. So same rule is being followed further as the chain length is increasing in these monosaccharides. Now the important friends hexoses are allose, altrose, glucose, mannose, glucose, mannose, glucose, idose, galactose and talose. You can remember then by using a mnemonics that all altruists gladly make gun in gallon tanks. So from all we mean altrose, all means allose. From altruist we mean an altrose. From gladly we means glucose. From make we understand mannose. From a gum we means a glucose. From a in means idose. Gallon means galactose and tanks means talose. So you can make your own mnemonics, but I can use this all altruist gladly make gum in gallon tanks. So these are aldehydic hexose. Aldehydic hexose. Out of all these structures, the simplest structure could be of allose, D-allose, because all the OH group in a D-allose is on the right side. You have to remember the structure of at least one of the sugar, that is glucose. In glucose, what happens is at carbon number 3, rest in D-glucose at carbon 3, the OH group moves to a left side, rest everything is fine. At carbon 3, the OH group moves to a left side, rest all are right side. While in case of mannose, what you find is the second and third carbon both are on left side. Here only third carbon was left side in glucose. In mannose, second and third both carbon is on left side. And one more structure if you can keep in your mind is the galactose, because these are three biologically important sugars. In glucose, third carbon is on left side. In mannose, second and third carbon is on left side. Then in galactose, third and fourth carbon is on left side. Third and fourth carbon is on left side. So third only on left side, then it is a D-glucose. Second and third both on left side, it is mannose. Third and fourth both on left side, then it is galactose. So these are 6 important aldehydic sugars, that is allose, altrose, then glucose, mannose, glucose, idose, galactose and talose. You can see that now these aldehydic hexose, they are having a 4 chiral carbon. So number of chiral carbon, they are increasing. In a triose aldehyde, it was 1. In tetrose aldehyde, there were 2 chiral carbon. In pentose aldehyde, there were 3 chiral carbon. In hexose aldehyde, now there are 4 chiral carbon. That is carbon 2 is chiral, carbon 3 is chiral, carbon 4 is chiral and carbon 5 is also chiral. Okay. Then if you have a look on ketohexose form. So first you can see that the number of chiral carbon is 1 lesser. So only 3 chiral carbon. Carbon 3, carbon 4 and carbon 5. Carbon 2 cannot be chiral because at carbon 2 you will have a ketonic functional group. You have to remember only the structure of one hexose, that is D-fructose. The structure of D-fructose is similar to the structure of D-glucose. That is, at third position you will have a OH group on left side. Only the difference is that now instead of aldehydic group, it is having a ketonic group. So glucose is a aldehydic sugar, while fructose is a ketonic sugar. Thus, the structurally it is almost same. So again, ketohexose is having 1 carbon lesser, 1 lesser chiral carbon as compared to the aldehydic versions. Now, Friends, coming to the point that what we mean by stereoisomers. Stereo itself means some three-dimensional space. So isomers in which the functional group or orientation of functional group varies in three-dimensional space could be referred to as stereoisomers. So we can say that stereoisomers have a same molecular formula. For example, there may be various stereoisomers of glucose, but all stereoisomers of glucose, whether it is a glucose or allose or altrose or D-glucose or L-glucose, all these stereoisomers, they will have C6, same molecular formula, C6H12O6. But only the difference would be that some OH group would be on left sides, while in some other sugars, the OH group could be on right sides. So basically, stereoisomers, they have same molecular formula and sequence of bonded atoms. That is same 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon, 6 and so on. It is in same sequence. But it differ in the three-dimensional orientation of their atoms in space. That how these atoms, they are arranged in a sequence, whether they are on left side or right side, how they are arranged, that is variable. Okay. So for example, all the aldehydic sugars, they will have this structure, that is CHO, then there would be C, you can say CH2 or CHOH, CHOH, this would be carbon 1, carbon 2, this would be carbon 3, this would be carbon 4, this would be carbon 5, and this could be carbon 6. But how these atoms are arranged in three-dimensional space, especially at the chiral carbon, that makes a difference. So differ in three-dimensional orientation of their atoms in a space. So for stereoisomers, the minimum criteria to be fulfilled is that it must have at least one chiral carbon, so that you can put some atoms on left side, some atoms on right side. So minimum criteria, what you need is that for stereoisomers, there must be, what is important is that for stereoisomers, there must be a one or more chiral carbon must be present. Because if there is no chiral carbon, means at somewhere you are having like this CHH, means this carbon will not be referred to as there is X and there is Y. This is not a chiral carbon. If you put H, this H to this side and this H to this side, it doesn't make any sense. But if there is some chiral carbon, let's say like this, CH and OH on this side, and now if you change the position, that is you take OH on this side and H on this side, it can generate some different type of molecule. So what you need is, you need a chiral carbon. Okay, you need some chiral carbon where all four functional groups, they are different. What could be the total number of possible stereoisomers? The formula is that 2 raised to power n. So in other words, number of possible stereoisomers, is 2 raised to power n, where n is number of chiral carbon. So if someone asks you what would be the possible stereoisomer of any aldopentose, for example, let's say ribose. So aldopentose, So answer would be aldopentose has number of chiral carbon in aldopentose is 3. Carbon second, carbon third, and carbon fourth. If there are 3 chiral carbon, then number of stereoisomers would be 2 raised to power 3. That is 8 stereoisomers is possible. Similarly, if someone asks you aldohexose, stereoisomers for aldohexose, like glucose, here the number of chiral carbon is 4. So 2 raised to power 4. Total 16 stereoisomers is possible. Similarly, if someone asks you about the aldo, instead of aldo we use term, let's say ketohexose, like fructose, someone asks you what would be the total stereoisomers for a fructose. So in ketohexoses, the number of chiral carbon would be 1 lesser than the aldehydic sugars. So N is 3. So 2 raised to power 3 will come out to be 8. Okay. So this is how you can predict the number of stereoisomers. So first, what are stereoisomers? The stereoisomers which are a same molecular formula, same sequence of bonded atoms. Only the positions of an atoms or groups varies in a 3-dimensional space. For stereoisomerism, any molecule must have 1 or more chiral carbon. Then let's move further. Stereoisomers could be broadly divided into 2 categories. That is, stereoisomers could be diastereoisomers or anisomers. That is, stereoisomers, these could be either mirror images of each other, and if they are mirror image of each other, they would be referred to as anisomers. And if they are not a mirror image, that is, 2 molecules, they are not a mirror image of each other, then they would be referred to as diastereoisomers. For example, D-glyceraldehyde and L-glyceraldehyde, they are mirror images of each other, they would be referred to as anisomers. Anisomers, they will have same name. For example, D-glucose and L-glucose, name is same, glucose. D-galactose, L-galactose. These are anisomers, so often designated as DL forms. While D-glucose and D-galactose or D-galactose and D-mannose, they are not mirror images of each other, and if they are not mirror images of each other, they are referred to as diastereoisomers. One of the class of diastereoisomers could be geometrical isomers, where there is change in the orientation of atom around some double bond, but that will not be applicable at least for the carbohydrates. Let's say this is one of the orientation, and if another orientation is like that, the CH2 is on this side and H is on this side, CH2 on this side, then such an diastereoisomers would be referred to as geometrical isomers. You can see that in this case, the CH2, they are on same side. In this case, one CH2 is on this side, another CH2 is on this side. These would be referred to as cis-trans isomers, but they will not be seen in carbohydrates. The diastereoisomers in carbohydrates could be epimers. Epimers is a special class of diastereoisomers where there is a change at single place. We will come to this point. If there is a change at single place, means any one chiral carbon, single place or single chiral carbon, then it would be referred to as epimer. And we will see that pentoses and hexoses, they can adopt a cyclic structure. And if they can adopt a cyclic structure, one more type of distereoisomers are possible, anomers, which are designated as alpha anomer and beta anomer. Okay, so let's study about these stereoisomers in little bit more detail. Now, the simplest stereoisomer is the enantiomers. What are enantiomers? Enantiomers are the non-superimposable mirror images of one another. So carbohydrates are said to be enantiomers if they are non-superimposable mirror images. So me and my mirror image, they cannot be superimposed, or you can say this right hand and left hand, these are the mirror images of each other. They cannot be superimposed on each other, because if you try to superimpose, what will happen? One thumb would be on this side, another thumb would be on this side. So these, which are mirror images of each other, these are the mirror images of each other, and these could be referred to as enantiomers. So in mirror images, not only on one finger, in all fingers positions has been changed. Thumb is on this side, first finger position has changed, second finger position has been changed, third finger position has been changed, fourth finger position has been changed. Here the thumb, you are starting with thumb, here you are starting with an small finger, index finger. Small finger, then middle index fingers, ring finger, middle finger, index finger, and the thumb. So orientation is almost, you can see, mirror of each other. Okay, so you are starting with the small finger. Here the small finger is at the last. Here the small finger is at the first. So these are two mirror images. Here the thumbs, they are first. In this case, thumb is small finger is first, thumb is last. Here thumb, you can see thumb is first and then it is last. So these are mirror images. So mirror images, they are designated as D form and L form. Again, D form and L form, they have nothing to do with optical rotation. D form doesn't mean dextrorotatory, or L form doesn't mean levorotatory. It is simply a designation, D or L form. The base molecule which is utilized for designation D or L form is glyceride. That is, in glyceride, since there is only one chiral carbon, and on this chiral carbon, if bulkier group, that is larger group, is on the right side, would be referred to as D form, and if OH group is on the left side, it is referred to as L form. All other enantiomers, they are named by comparing their structures with D-glyceride and L-glyceride. Whether they are amino acid or they are phospholipid or they may be any other molecule. The enantiomers, for enantiomers, the reference molecule is D-glyceride and L-glyceride. So on a chiral carbon, if OH group is on right side, it would be referred to as D form, and on chiral carbon, if OH group is on left side, this would be referred to as L form. From OH group, we mean the bulkier group. For example, if we see an amino acid, so this is a functional group, this is a chiral carbon. On chiral carbon, in this case, H is on this side, NH2 is on this side. If bulkier group is on right side, it is referred to as D form. And if NH2 group is on left side, this is referred to as L form. What you find is that these D form of sugars, and L amino acids, they are more common in biological system. We are not saying that other form cannot be there. Other form may be there, but the major sugars which we find in biological system are D form, and major percentage of the amino acids what we find in biological system is in the L forms. From structural point of view, you find that the D form of sugars, they are thermodynamically more stable. So with time, the L form, even if they may be there, they are coming to a stable form, that is referred to as D form, and L form of amino acids, thermodynamically they are more favorable as compared to the D form. So with time, the unstable form would be converted into a stable form. So what you find is the D form is more stable for the sugars and L form is more stable for the amino acids, especially in under oxidative environment in biological system. So what are enantiomers? Enantiomers, they are simply mirror images of each other. So D-glucose and L-glucose, where all OH group would be, all positions of all OH group at chiral carbon will change, would be referred to as enantiomers. D-erythrose and L-erythrose would be enantiomers. Now friends, a molecule may have more than one OH group, more than one chiral carbon, where the positions of OH group may be variable. Then how to compare it with a D-glyceraldehyde or L-glyceraldehyde? My dear friends, for example, this is the structure of glucose, which is having carbon second is also chiral, carbon 3 is also chiral, carbon 4 is also chiral, carbon 5 is also chiral. If we try it to compare with a glyceraldehyde with a third chiral carbon, you will say that OH group is on left side. It should be referred to as L-glucose. And if you compare carbon second, carbon 4 or carbon 5, the OH group is on the right side. You will say that this is a D form. So what to do? Which carbon has to be compared? So whenever there are more than one chiral carbon, then we have to compare last, or we can say position at last chiral carbon, or we can say that penultimate carbon. So in glucose, this is the first chiral carbon, this is second chiral carbon, this is third chiral carbon, this is fourth, that is the last chiral carbon. Or you can say that this is the ultimate carbon, this is the penultimate carbon. So you have to compare this position with a D or L glyceraldehyde. If at this place a OH group is on the right side, we will say that it is a D form of glucose. So whenever there is more than one OH group, we have to compare a last chiral, or we can say second last carbon, which is also referred to as penultimate carbon. If this is D-glucose, then what would be the L-glucose? It would be a mirror image. And mirror image doesn't mean that only the position at fifth carbon will change. No. Position at fourth carbon will also change, position at 3 carbon will also change, position at second carbon will also change. That is, in mirror images, the position of functional group at all the chiral carbons, they get altered. So one is referred to as D-glucose and another is referred to as L-glucose. So let's say if someone says you, what is this sugar? This is a D form or L form? If someone asks you, this is the case. Simply you have to say whether it is a D form or L form. This is 6 carbon sugar. Simply you have to tell whether it is a D form or L form. These are the chiral carbon. This is the first chiral, this is second chiral, this is third, this is fourth. Yes, answer would be L form. Why L form? Because you have to look at the last chiral carbon, and at the last chiral carbon OH group is on the left side. You will say that this is the L form of sugar. Although here OH group is on right side, here OH group is on left side, here OH group is on right side, you have to compare the last chiral carbon. On basis of that only you will able to tell that this is the L form of sugar. You don't know the name, that's fine, but at least you can say that it is the L form by looking at the structure. Always keep in mind that the molecule should be drawn in a fashion that functional group should be at top. Okay, start with the functional. It should not be like that functional group is at the bottom. If it is the case, then rearrange the molecule such that the functional group is at top. Then only you will able to tell whether it is a D form or L form. Now friends, all molecules, they need not to be a mirror image. If the stereoisomers, they are not the mirror image, then they are another type of stereoisomer referred to as distereoisomers. So in distereoisomers, there is change in orientation of atoms in 3D space at one or more chiral carbon, but not at all chiral carbon. If it would have been at all chiral carbon, then it would be mirror image. So we are saying that there is a change that could be on one carbon, that could be on two carbon, that could be on three carbons, but it is not on all the carbons. And if it is not at all the carbon, then it would be referred to as distereoisomers. So if you compare the structure of D-mannose and D-galactose, what you find is the position, this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. You find that the position at carbon second has changed, carbon third, there is no change, carbon 4 has changed, carbon 5 there is no change, and so on. So there is a change at two different places. If it would have been at all the places, then it would have been the mirror image enantiomers, but there are changes at two places. So this would be simply designated as a distereoisomer. Okay. Now there is a special class of distereoisomers that is referred to as epimer. So what are epimer? So epimer are distereoisomers where change in the orientation of atoms in 3D space is at single chiral carbon. So it is at single chiral carbon, because we have said that in distereoisomers the change could be at one or more than one place, but not at all places. But if it is only at one place, then such a distereoisomer would be referred to as epimer. If it is single place, epimer. If it all place, then it is not a distereoisomer, then it would be an enantiomer. For example, if you compare the structure of D-glucose and D-mannose, so this is 1, 2, 3, 4, 5 and 6. This is the structure of glucose, and if you compare the structure of D-glucose with a D-mannose, what you find is that there is change at only carbon 2. Rest of all carbon are like a glucose. So that's why we say that D-mannose is C2 epimer of glucose. What this means to us? That mannose is like a glucose except carbon second, where there is a change in position. Similarly, in an allose, what you find, it is like a glucose except the position 3. So you can say that D-allose is C3 epimer of glucose, or even vice versa is also true. You can say that glucose is C3 epimer of allose. And similarly, if you look at the structure of the galactose and compare it with the glucose, there is change at only 4th place. So you will say that D-galactose is C4 epimer of glucose. This is very important. At least these three structures you must know. These atomic structures you must know, because question has been asked in variety of examination, and even it could be asked in your exam as well. So just have a look on the structure of D-glucose, D-mannose, allose and galactose. That's what you have to remember, at least from the structural point of view. So let's move further. Now, basically, the 5 carbon or 6 carbon sugar, they rarely occur in this form. This form which is drawn is the chain form. They rarely occur in a chain form. They get convert into a stable ring form. That if there is a 5-membered heterocyclic ring, then it is referred to as Pyranose. Sorry, 6-member heterocyclic ring is referred to as Pyranose, while 5-membered heterocyclic ring is referred to as Furan. That is, what you find is that aldopentose and ketohexose. For aldopentose and ketohexose, the stable ring structure which is formed is they adopt a furan ring. For aldehexose, the stable ring which is formed by them is referred to as pyran. Now, basically, the reason for the formation of pyran or furan ring is the fact that the aldehyde and OH group, they are very reactive. They have a tendency to form a hemiacetals. Similarly, ketone and OH group, they are also very reactive. They have a tendency to form a hemiketals, which is the reason why there is a formation of pyran or furan ring. So, what we are saying that aldehyde and OH group, they have tendency to form a hemiacetals, and ketone and OH group, if they are in front of each other, they have a tendency to form a hemiketal. So, hemiacetals or hemiketals. So, this is the chain form which generally tend to adopt in a ring form. So, whether ring form would be favored or chain form would be favored, that depends upon which is thermodynamically more favorable. For example, if delta G0 value is negative, what this means is that comparatively ring form of glucose is more favored as compared to chain form. You will find that 99% would be in this form and only 1% would be in a chain form. Okay. So, you can have a look. What is happening is that this OH group, which is on 5th carbon, it is interacting with an aldehyde group which is 1st carbon. In general, during the formation of ring, no net loss of bond or atom is observed. Only there is a rearrangement of atoms or bonds. This hydrogen, which was with this OH group, this get attached to this oxygen. From this OH, it moves to this. This double bond which is between C double bond O. It is now forming a this double bond get into single bond, and one more bond is formed between carbon 1 and carbon 5, which is observed over here. So carbon 1 and carbon 5, they start forming a one new bond. While at carbon 1 there was C double bond O, and that C double bond O, now there is only C single bond O, and with there is one more hydrogen, and this hydrogen is being taken from carbon number 5. So simply there is a formation of this ring structure. Now once this ring structure is formed, you can see that now the carbon 1 also become chiral. This carbon 1 also become a chiral, because at this carbon, this functional group is different, this OH group is different, this is group different, this group is different. One more chiral carbon is seen when there is a formation of ring structure. So that's why even there is a formation of diastereoisomers for a ring structures, which are referred to as anomers. So if this carbon 1 in aldehyde or carbon 2 of ketone is referred to as hemiacetal or hemiketal carbon, because these are the place where there is a functional group is present. They are also referred to as anomeric carbon. They are also designated as anomeric carbon. Since I have said that this ring form could convert back into a chain form, if ring form, let's say if it is more than 99%, it could be converted back into chain form. It means this bond will break, so that again a chain form could be formed, and chain form could convert back into a ring form. Whenever a chain form get into ring form or ring form convert to chain form, again chain form convert to a ring form. Under this condition, it is not always say that always a condition that OH group would be down the plane. The condition may be different, means it is not always a case that OH group would be down the place. Sometimes OH group could be above the place. So this, and at anomeric carbon, that is hemiacetal or hemiketal carbon, the position of the atoms in a 3D space, they can also vary. OH group could be down the plane, OH group could be above the plane. So that's what I want to say. Similarly, the 5 carbon, that is aldopentose, they form a 5-membered ring that is referred to as Pyranose. Here now the attack is by 4th carbon. In this case, the attack was by the 5th carbon. There was formation of 6-membered ring. In 6-membered ring, there were 1, 2, 3, 4, and 5 were carbon, and 6th was oxygen. That's why we are using term heterocyclic. While in 5-membered ring, you can see that there are 4 carbon, 1, 2, 3, and 4 carbon, and 5th one is oxygen. That's why again it is a heterocyclic ring. But there are 5 members. That's why it is referred to as furan ring. So again, in this case, the 4th carbon it attack, so it is being drawn over like this. This 4th carbon OH group it attack at the 1st carbon, such that this bond gets shipped over here. Here comes a hydrogen, and one new bond would be formed over here, which is being represented. This is a new bond which has been formed. Again, this OH group could be down the plane, or this may be a scenario that during the closure for second time, the OH group over here could be above the plane. This may be the case. Okay, these two different possibilities are there, this or this. If OH group is above the plane at anomeric carbon, this would be referred to as beta D ribofuranose. And if OH group is down the plane, it is referred to as alpha D ribofuranose. So alpha and beta are anomers. What are they? They are anomers. So aldopentose, they adopt a furan ring. So aldohexose, they form a pyran ring. That's what we have seen. That's why we have named it as glucopyranose, alpha D glucopyranose. And the aldopentose, they form a furan ring. For example, alpha D ribofuranose. Now, fructose, which is a ketonic sugar, that is, this is ketohexose. Example is fructose. Fructose could form a 6-membered ring where there is an attack by 6th carbon on 1st carbon, sorry, on 2nd carbon, because anomeric position in a ketone is 2nd. If it is like this, then in the ring you will find carbon 1, carbon, the 2nd carbon, this is 3rd carbon, this is 4th carbon, this is 5th carbon, and the 6th would be oxygen, which would be in a ring. That is being observed. Carbon 1, this is 2nd carbon, 3rd carbon, 4th carbon, this is 5th carbon, and one more is the oxygen. 6-membered ring is being formed, which is referred to as fructopyranose. Since at this position, at alpha position, OH group is down the plane, it is referred to as alpha D fructopyranose. So this is the carbon 1, this is carbon 2nd, 3rd, 4th, 5th, and 6th. So fructose being a ketone, so ketohexose can adopt pyran ring. But the pyran ring which is adopted by these ketonic version, it is unstable. It is unstable. So this is the form of the, because you know fructose is one of the natural known sweetest sugar. This is the form which is present in honey. So fructopyranose, this provide a sweet taste to honey. But we know that with a time, the honey loses its taste. Or if you heat the honey, the taste of honey get altered. Why so? Because this fructopyranose is an unstable structure with a time or on heating or improper storage, that is in presence of sunlight. Often honey is kept in a brown bottles. So if honey get exposed to the sunlight, if it is kept at higher temperature, or even with a time, means it has been stored for a very long period of time, the fructose may adopt a stable structure referred to as furan structure. So fructofuranose, this is the stable structure of fructose. Here you can see that now 5th carbon, instead of first 6 carbons was attacking, now 5th carbon is attacking on the 2nd carbon. Now this is carbon 1, this is carbon 2, carbon 3, carbon 4, carbon 5, and this is carbon 6. The structure, because OH group is down the plane at anomeric carbon, it is referred to as alpha D fructofuranose. But this stable structure of fructose, it is not as sweet in taste as fructopyranose. So that's why we say that with time or on heating, the fructose loses its taste. Okay. So basically, taste resides in the structure of a sugar. If any other molecule X, Y, Z having a structure similar to the fructopyranose, it will bind to our receptors present on taste buds for the sensation of sweet. will give a information to the brain that we have taken something sweet. Even these could be some artificial sweetener like aspartame. Now, as we were saying that these 5 carbon or these 6 carbon sugars, they adopt a ring structure, and ring structure is in a state of opening and closing. That is, chain form could convert to a ring form could convert back into chain form could convert back into ring form. During this, at this anomeric carbon, OH group could be down the plane or OH group could be above the plane. This first carbon is referred to as carbon 1 of aldehyde, as we have already mentioned, or carbon 2 of ketones is referred to as hemiacetal or hemiketal carbon. It is also referred to as anomeric carbon. And at this anomeric carbon, 2 different possibilities there, that is alpha orientation. That anomeric carbon, OH group is down the plane, then it is referred to as alpha anomeric form, or it may be beta anomer, that is where OH group is above the plane. And out of this alpha or beta, for example, this is the structure of alpha D-glucopyranose and this is the structure of beta D-glucopyranose. So what you can see is that the change is only at anomeric carbon. So we said that 1% could be a chain form and 99% would be the ring form. But ring form of glucose, again, it could be in 2 different versions. It could be alpha anomeric form or it could be beta anomeric form. But out of this alpha and beta anomeric form, which would be more, again, it depends upon a stability. What you'll find that approximately only 33% is alpha D-glucose and 66% is there in form of beta D-glucose. That is almost in a ratio of 1:2. Probable reason is beta anomeric form is more stable, thermodynamically more stable as compared to an alpha glucose or alpha D-glucose form. Are you getting this? Okay. Now, if you keep 100% alpha D-glucose in a test tube, you will find that with a time, some portion of alpha D-glucose has been converted to a stable beta D-glucose. And if you put 100% beta D-glucose, then also it will, some proportion of this will convert to an alpha D-glucose, and finally you will get an equilibrium ratio of 1:2. That is 33% would be alpha D-glucose and 66% would be beta D-glucose. Okay. That is, whenever you will disturb equilibrium, as we have studied in Le-Chatelier's principle, whenever you will disturb a equilibrium, the reaction will proceed in the direction so that same equilibrium could be achieved back. So if you are putting all alpha D-glucose, the equilibrium will shift toward the formation of beta D-glucose. If 100% beta D-glucose is there, the equilibrium should toward formation of alpha D-glucose until alpha D-glucose and beta D-glucose obtain the equilibrium ratio of 1:2. And after this, there will be no change because now there is an equilibrium, that is forward rate is equivalent to backward rate. So this phenomenon where alpha D-glucose could convert to beta or beta could convert to alpha until an stable equilibrium ratio is achieved is referred to as mutarotation. Okay, let's move forward. Now, my dear friends, as I have already mentioned that D-glucose and L-glucose doesn't mean that they are dextrorotatory or L or levorotatory. D or L form, they represents an absolute configurations. They do not provide you any idea about an optical rotation. So do not confuse D form with a dextrorotatory or L form with a levorotatory. There is no correlation between a D form and optical rotation. So basically D and L indicate configuration of the molecules or atoms at a symmetric carbon. They do not indicate about anything about how they are going to rotate the plane polarized light. For example, D-fructose rotate a plane polarized light by plus 52 degree, means if it is plus means it is a dextrorotatory, and the D-fructose it rotates optical plane polarized light by in anti-clockwise direction by minus 92, so it would be referred to as levorotatory. So you can see that D form could be dextrorotatory, D form could be levorotatory. There is no correlation. 50% you would be right and 50% you would be false. Okay. So D-fructose or D-glucose, they are simply representing the absolute configurations. They are not representing the optical rotation. Optical rotation is represented by symbol plus or minus, or in older books you can find a small d for the dextrorotatory and small l for levorotatory, but it's never you will use capital D or capital L. So plus or D, this represents a dextrorotatory, and minus or L represents a levorotatory, while capital D and capital L, they represents an absolute configurations. They represents absolute configuration. Okay. So capital D and capital L, you cannot predict about the optical rotation, but simply what you can say that capital D and capital L are the enantiomers which has same physical properties, like the physical property of D-glucose would be similar to an L-glucose. Only the difference is that if D-glucose is dextrorotatory, L-glucose would be levorotatory. That what you can say. If D-fructose is levorotatory, then you can say that then L-fructose must be dextrorotatory. There is no correlation, but at least if you know about the one form, you can predict about other form, because both these forms are mirror images. So if D-glucose is dextrorotatory, you find it through a polarimeter, then the optical rotation of L-glucose would be also same. If D-glucose is plus 52, then definitely you can say that L-glucose would be minus 52. If D-fructose is minus 92, you can definitely say that L-fructose must be plus 90. That is, enantiomers, they rotate the plane polarized light in a opposite direction, but in which direction you cannot predict. But if you know that one of the enantiomeric form is dextrorotatory, then definitely another enantiomeric form, that is mirror image of that, would be a levorotatory. That's it. But there is no direct correlation between D form and L form. So what we mean by optical activity? So if there is some sample, and if through a sample, if you pass a plane polarized light, so let's say there is a light source, this is normal light where the particles, they are oscillating in all possible planes. When it is passed through a polarizer, now particles, they are oscillating only in one place. All the light particles, they are oscillating only in one plane, that is once it passed through a polarimeter. Then this plane polarized light is allowed to pass through an optically active substance. So there is some optically active substance over here which is kept in the path of plane polarized light. If substance has one or more chiral carbon, it is definitely going to interact with a plane polarized light, and if it interact with a plane polarized light, that definitely there would be some change in plane of polarization. So the plane polarized light, it moves out of that sample, still it remains a plane polarized, means still all the particles, they are propagating in a same plane, but the plane of polarization has changed in reference to previous condition. First the plane of polarization is like this, and now the plane of polarization is like this, means there has been some rotation. That is, let's say this is the plane polarized light, it is traveling like this through the sample. Once it passes through sample, now all particles, they are oscillating like this. Still they are plane polarized light, but they have rotated. Now rotation could be in anti-clockwise direction, rotation could be in a clockwise direction. On basis of this, the molecules, they are either referred to as levorotatory or dextrorotatory. So to predict whether the substance is optically active or optically inactive, what you have to do is you have to utilize either polarimeter, or you have to use an optical rotatory dichorism, referred to as ORD, or further higher techniques which could be utilized would be circular dichorism spectroscopy. All these techniques, they are depend upon the optical activity. Okay, so dextrorotatory, the symbol is plus. They rotate the plane polarized light to the left, sorry, to the right, and levorotatory, they are minus, they rotate the, so dextrorotatory is which are rotating the plane polarized light in a clockwise direction, or which is also referred to as to right, or levorotatory, which rotate in an anti-clockwise direction, also referred to as left. Symbol for levorotatory is minus, for dextrorotatory is plus. Now just think what will happen if you put an equimolar concentration of D form and L form, or if you add a equal substance of dextrorotatory and levorotatory. Obviously it will behave as a racemic mixture. What is racemic mixture? That it may contain more than one optically active substance, but the optical rotation of one molecule is cancelled by the optical rotation of another molecule. So what I want to say is that if you put let's say D-glucose, whose optical rotation is plus 52 degree, and you take L-glucose as well, and definitely its optical rotation would be opposite to this, that is minus 52 degree, and if you add in equal amount, and you pass it through, you pass a plane polarized light, there would be no rotation. The optical rotation would be 0 degree, although there are two optically active substances. Such a mixture would be referred to as racemic mixture. So whenever you take a equal concentration of D form or L form, it will, the optical rotation of one form will cancel the optical rotation of another form. Such an condition is referred to as racemic mixture. Okay, let's move further. Every molecule has its a specific optical activity by which it can be identified. So specific optical rotation, that is at certain wavelength and at 25 degrees centigrade for any molecule. For example, for D-glucose we are saying again and again it is plus 52 degree, or for D-fructose we are saying that this is minus 92. By this it could be identified that it is a D-glucose or D-fructose. Different molecules, they have different values. The specific optical rotation, that depends upon the observed optical rotation. Observed optical rotation could be variable depending upon the optical path length, that is what is the path of light travel through that optically active substance. Often the path length is taken in decimeter. Okay, so 1/10 of meter would be referred to as decimeter. Then concentration of the optically active substance, and the concentration is taken in gram per ml. Or in other words, we can say that observed optical rotation would be equal to specific optical rotation, which is fixed. multiplied by optical path length multiplied by concentration of molecule. That would be the observed optical rotation. That is, what optical rotation you will observe, that depends upon the specific rotation of that particular molecule, what is the optical path length what you have taken, and what is the concentration of molecule. Because the standard specific rotation is when you are taking a concentration of 1 gram per ml of solution, path length of 1 decimeter. But always this would be the case, is not necessary. That's why observed optical rotation could be variable. Now, as I have said, that in a chain form which is unstable, it readily get converted into a ring form. In a ring form, let's say 99%, there are two different forms possible. One is beta D form and another is alpha D form, where anomeric carbon could be above the plane and anomeric carbon could be below the plane. So what we have drawn some up to like this, that these two different forms could be obtained, alpha form and beta form. These two forms could be adopted for a glucose. So let's say this is the structure of glucose. So let's say this is the structure of glucose. If OH group is down the plane, it is referred to as D form, and if it is above the plane, it would be referred to as, it is down the plane, it is referred to as alpha form. It is above the plane, it would be referred to as beta form. So alpha form and beta form both will be there almost 99%. And as we have said that these would be in these two different forms would be in an approximate ratio of 2:1. That is, beta anomeric form would be more as compared to an alpha anomeric form. Why so? The reason is again the stability. We are trying to draw the ring structures assuming that the glucose is planar. But my dear friends, whether it's a furan ring or whether it is a pyran ring, in carbohydrates they are not planar. That is, all carbon, they do not lie in a same plane. The 6-membered ring, it tend to adopt a stable chair form. It tend to form a stable chair form. That is, out of the 6 carbon, 1 carbon is above the plane, another carbon is down the plane. So instead of getting all 6 members in a same plane, one is out of plane, another is down the plane. One is exo and another is endo. So only one thing you have to keep in mind, that furan or pyran ring in sugar is not planar. All carbon and oxygen atoms, they do not lie in a same plane. The ring form, in a ring form, the more stable structure is the chair form. If it is a pentose sugars, there is 5 carbon sugars, they form furan ring, and furan ring, the stable structure is half chair form. Again, that is not planar. Now in chair form, 2 different orientation is possible, where OH group at anomeric carbon could be above the plane and OH group could be down the plane. When OH group is above the plane, that is referred to as beta anomeric form, which is 63%, and when OH group is down the plane, it is referred to as alpha form, which is approximately 36, or you can say 36%. Almost, in other words, they are almost in a ratio of 2:1. But why this beta form is more as compared to alpha form? The reason is that this structure is more stable. Why this structure is more stable? Because in beta anomeric form, this OH group is equatorial. It is like this. This is equatorial. OH group means this is the chair and this is an equatorial form, which forms a more stable structure in a chair form. In alpha anomeric carbon is OH group is like this down the plane, means it is axial. So let's say this is the chair and this is the OH group, it is in the same plane. If its OH group is like this, you will say that it is axial. So when OH group is axial, it decreases stability. If OH group is equatorial, as it is seen in beta D glucose form, this makes a structure relatively more stable. So that's why out of alpha D glucose and beta D glucose, which form is more prevalent? Beta. So at equilibrium, we are saying that beta anomer of D glucose is dominating. Why? Because OH group of the anomeric carbon is more stable in equatorial position. Which position? Equatorial position, as compared to the axial position which is seen in the alpha anomeric form. So this, if you put 100% alpha D glucose, it will also convert to a beta D glucose, or if you put 100% beta D glucose, some proportion of it will convert to alpha D glucose. This rotation is referred to as mutarotation. And what is, you can say, the proof that this mutarotation happens? The proof is that optical rotation of alpha D glucose, if alpha D glucose, more accurately gluco in a ring form, so we will name it as alpha D glucopyranose, its optical rotation is 100. If it is 100% this form, if it is in this form, it's pure, its optical rotation is plus 112.2 degree. And if it is a beta D glucopyranose, 100%, if it is this form, its optical rotation is plus 18.7 degree. So both these form of glucose, they are dextrorotatory, and that's why glucose is referred to as dextrose, while fructose is referred to as levulose. Both forms, they are dextrorotatory, but beta form is lesser dextrorotatory as compared to an alpha form. If glucose would have been 100% in alpha D form, then the specific optical rotation of glucose would have been 112. And if 100% of the glucose exists in a beta D glucopyranose form, then optical rotation of a glucose would have been 18.7. But what you find is neither 112 nor 18.7. Whenever you find a glucose solution, it shows an optical rotation of approximately plus 52.7 degree. Means neither it is 112 nor it is 18. It has declined from 112, but not has declined up to 18. If it would have been declined up to 18, then you will see that 100% alpha has been gone to beta. Somewhere in the middle it stops. So that's what you observe, that if you in a test tube, if you take 100% of an alpha D glucose, this is 100% alpha D glucose, and immediately you pass a plane pose light, optical rotation is 112.2 degree, which suggests that it is a pure alpha D glucose. But with a time, after some time, let's say after 1 hour, if you again pass up light, you find that now the positive dextrotation value has declined and it becomes stable at plus 52.7 degree. Same if you start with in test tube, if you take with a beta D glucose, initially when you pass a plane pose light, what you find is the optical rotation is around plus 18.7. If no change occurs, it should remain plus 18.7, but after some time when you pass, it increases and attain a value of plus 52.7. This also attain 52.7, this also attain 52.7. So its optical rotation value is declining, its optical rotation value increases, and both these test tubes, they adopt the same value, that is plus 52.7. This suggests that once an optical rotation is at 52.7, a stable equilibrium has been attained. Okay, so that's why we say that glucose has an optical rotation of plus 52 degree, assuming that almost around 63% would be the beta D glucose and around 33% or 34% would be the alpha D glucose. Okay, So that's why D-glucose, for D-glucose we say that it is 52.7, assuming that some would be alpha D-glucose form and some form would be a beta D-glucose form. So alpha D-glucose is converted to a beta D-glucose, and beta D-glucose could be converted to alpha D-glucose. This is referred to as mutarotation. So let's apply your mind on this question, which is based on mutarotation. The question is, the enzyme glucose oxidase acid from mold Penicillium notatum catalyze the oxidation of beta D-glucose. It oxidize the beta D-glucose to D-gluconolactone. This enzyme is specific for beta diastereomers. Enzyme name is glucose oxidase. And then how it is being utilized for blood glucose estimation? Because it is not acting on alpha D-glucose. The enzyme cannot act on alpha D form. Then how you can say that this method is appropriate for estimating the blood glucose? Because logically it should measure only the beta D-glucose in a blood. It should not able to measure the alpha D-glucose. But we say that this is the efficient method. The reason is that as they are in a ratio of 1:2, means let's say 63% is this and 36% is this. If this is being removed, its percentage will decline, and if its percentage will increase, so alpha D-glucose will come to beta D-glucose, so that again the same ratio could be obtained. So as you keep on disturbing equilibrium, how you are disturbing equilibrium? By removing the beta D-glucose, the alpha D-glucose will being converted into an beta D-glucose, and there would be time that 100% of this has been converted to a gluconolactone. Alpha D-glucose would have been converted to beta D-glucose. So as you remove the beta D-glucose, alpha D-glucose get into beta D-glucose, and further beta D-glucose will be converted into gluconolactone. So in this way you can assess the total blood glucose. Now there are some modified, or you can say derived monosaccharides. So derived monosaccharides are those which do not obey the formula CnH2nOn. They may have some extra groups or extra atoms besides carbon, hydrogen, oxygen, such as you can find nitrogen, you can find sulfur, etc. So such sugars would be referred to as derived sugars. The simplest derived sugar is referred to as glycosides. So if any glycone means which is not a sugar, it get form a glycosidic bond, means it get attached with a sugar. This is the sugar. Then it is referred to as glycoside. Now this could be a nitrogenous base glycoside, referred to as nucleoside. It could be a steroid. A glycone could be steroid with a sugar, referred to as steroid glycoside, and so on. The bond which is formed is referred to as glycosidic bond. Glycosidic bond could be N-glycosidic bond, or glycosidic bond could be O-glycosidic. So sugars having added some non-sugar moiety, then it would be referred to as glycosides. For example, if glucose is there and then it is attaching with some, it would be referred as glucoside. If galactose is there, it is attaching with a glycone, galactoside. If ribose is there, it is attaching with some glycone, it would be referred to as riboside. Similarly, there could be sugar acids. Example of sugar acid could be, let's say, you know this, probably you know this structure. So this is the structure of D-glucose. And at this place, that is at first place, you are having a COOH. Instead of CHO, you are having a COOH group. Then this is a sugar, acidic sugar. Now this would be referred to as acidic sugar, and the name of that acidic sugar is gluconic acid. This is an acidic sugar derived from glucose, referred to as D-gluconic acid, or simply if this H get D proton, it is like the CO minus, then it could be referred to as gluconate, D-gluconate. If its condition is like the CHO, here this is C, then again carbon 5, this 6. Again, this is the structure of glucose, and at 6th position, if you are having a acidic group over here, then now it is referred to as D-glucouronic acid. D-glucouronic acid or D-glucouronate. So D-glucouronic acid, D-gluconic acid. Similarly, there could be a galactouronic acid. In galactouronic acid, what will happen? Yes, you know, if it is like this, CHO, COH, H, COH, H, COH, H, COH, H, and here if you are having a COH, this OH group is on this side, it would be referred to as D-galactouronic acid. Okay, so example of sugar acid is gluconic acid, glucouronic acid, galactouronic acid, even ascorbic acid, which is vitamin C, is an example of sugar acid. Vitamin C, it is also a sugar acid. So basically these are the oxidized form of sugar: gluconic acid, glucouronic acid, galactouronic acid, ascorbic acid. Similarly, there could be amino sugar. For example, you know, this is the structure of, okay, this is the structure of glucose. Sorry, this is the structure of glucose. This is D-glucose, and OH groups down the plane, you can say alpha D-glucose. But if you add a NH2 group at the second position, if there is an NH2 group at the second position, now it would be referred to as amino sugar. This is now referred to as alpha D-glucose amine. Alpha D-glucose amine, amino sugar. Similarly, there could be alpha beta, that is anomeric form. Similarly, you can have alpha D-galactose amine. So galactose amine structure would be somewhat like this. Only at this place you will find NH2, OH group above the plane. If it is galactose, at 4th place OH group would be also above the plane. This is first carbon, this is second carbon, third carbon, fourth carbon, fifth carbon, and sixth carbon. This is the structure of D-galactosamine. Similarly, at this place you can have a acetyl group as well. Let's say this is the structure of galactose. Okay, this is the structure of alpha D galactose. At this, if you put an NH2 group, this become galactosamine. If you further add an acetyl group to this, acetyl group is C double bond O CS3. This is an acetyl group. Then you will say that now it is a structure of N-acetyl D-galactosamine. So alpha D glucosamine, galactosamine, manosamine, N-acetyl galactosamine, N-acetyl. Similarly, you can have N-acetyl D-glucosamine. These all are example of amino sugar. Ribosylamine, that is amine of ribose. So sugars could be amino sugar. Then sugars could be deoxy, which are having one lesser oxygen. So let's say this is the you can easily identify the sugar, I think. You must be able to recognize at least this sugar. This is D glucose. Okay, or if OH group is down the plane, you can say alpha D glucose. But if you, this is carbon 1, this is carbon 2, this is carbon 3, 4, 5, 6. If you remove OH group at this from this place, what will happen? A well-known molecule which is in very limelight nowadays, you would have heard its name in reference to DRDO, this molecule. Where now there is only H instead of OH. Yes, the name of this molecule is, can you predict? So if you're not putting anything, means there is a hydrogen. Okay, this is first carbon, this is second carbon, third carbon, fourth carbon, fifth carbon, sixth carbon. This is glucose, but at this place now instead of OH there is only H. So this is, yes, 2DG, that is 2-deoxy glucose, believed to be playing an important role in controlling the growth of coronavirus, especially in alveolar epithelial cells. 2DG, a mimic of glucose. Similarly, this is the structure of, this is 5-membered ring structure. That's it. This is a 5-membered ring structure of beta D ribose. This is first carbon, this is second carbon, this is third carbon, this is fourth carbon, this is fifth carbon, where there is CH2OH. If you put OH and simply H on this place, then 1, 2, 3, 4, 5. This is one well-known deoxy sugar present in DNA, referred to as 2-deoxy ribose. Similarly, you can have this kind of structure as well, that you will study in much detail in molecular biology, which leads to chain termination, inhibit the replication process. This is 2,3-dideoxy ribose. Dideoxynucleotides, they have this kind of sugar, dideoxy ribose. This is 2, this is 3, this is 1, this is 4th, and this is 5th. Okay, so these are referred to as deoxy sugars. Okay, 2-deoxy glucose and so on. Similarly, my dear friends, there could be modified sugars referred to as alcoholic sugar, where instead of CHO you are having a OH group, then it would be referred to as alcoholic sugar. For example, this is a structure you know. This is glyceraldehyde. Now here if you are having CH2OH even at this place, glyceraldehyde, this is the structure. Now again you should know this structure. This was glyceraldehyde. This is referred to as glycerol or simply glycerol. So glycerol is sugar alcohol, that is instead of aldehyde now there is a OH group. Similarly, from mannose you can obtain mannitol. From ribose, alcoholic sugar which can be obtained is ribitol. So glycerol, mannitol, ribitol, etc. These are the sugar alcohols. Okay. Then the sugars could be referred to as reducing or non-reducing. Any sugar which has a free aldehyde or free ketone group are referred to as reducing sugars. So because all those sugars which has a free aldehyde or free ketone group, they can reduce the Benedict reagent or Fehling solution. In both these, Benedict solution, Fehling solution, copper is in Cu2 plus state, that is it in cupric state. If there is some reducing sugar, if sugar is reducing, if reducing sugar is there, reducing sugar obviously it will give an electron. That's why sugar is referred to as, means it is a sugar which is capable to donate an electron, which can reduce others. It will get into Cu plus. To donate an electron, sugar must have a free aldehyde or ketone group. Even if it is in a ring structure, we will say that it is a free. Okay, ring structure means doesn't mean that it is participated in bonding. Means hemiacetyl carbon, hemiketyl carbon, or the aldehyde or ketone group is free. It is not involved in bonding. We will say that it is able to reduce the Benedict reagent or Fehling reagent. So whenever the Cu2 plus form, which may be in a sodium citrate or it may be in a sodium tartrate. If in sodium citrate, it is referred to as Fehling Benedict solution. If it is in a sodium tartrate, it is referred to as Fehling solution. So Cu plus, if it happens, then there is a change in color. The change in color, the change would be a brick color, final color would be brick red. So there is a test tube where you are having Benedict reagent. If you put some sugar, unknown sugar to it, if a color changes to brick red, you say that it is a reducing sugar. So all monosaccharides are reducing sugars, obviously, because they are not forming glycosidic bonds, thus have free aldehyde or ketone group. So they must be referred to as reducing sugar. Various disaccharides can be reducing, like lactose, maltose, etc. Where in disaccharide there are two sugars. One of the sugar is involved in bonding, but other sugar, a second sugar, may still have a free anomeric carbon, or they may be non-reducing, like sucrose, trehalose, etc. So can be reducing, can be non-reducing for disaccharides or oligosaccharides. But monosaccharides, these are reducing sugars. Okay. Now moving to the higher version of sugars, polysaccharides, and the simplest polysaccharides are oligosaccharides. Oligosaccharides are those, or these are the simple polysaccharides, where the number of monosaccharides are 2 to 20. So the simplest, if there are only two sugars which are linked by a glycosidic bond, it would be referred to as disaccharide. If there are three sugars, they are linked by glycosidic bonds, then it would be referred to as trisaccharide, and so on. Okay. So the sugars which has the number of sugars ranges from 2 to 20, they are referred to as oligosaccharides. These could be tri, tetra, hexa, hepta, etc. So linkages, glycosidic bond. Yeah, more accurately referred to as O-glycosidic bond. Basically, it is an ether bond. That is, whenever there would be formation of bond, glycosidic bond, what you'll find is there would be OH from one side and H from another side would be involved in bonding. So let's say this is some sugar. This is anomeric carbon. That is, anomeric carbon has to participate at least from one side. Okay. So this is first carbon, which is an anomeric. It is not necessary that anomeric carbon participate from both sides. So let's say first carbon participating from one side and fourth carbon is participating from another side. And often you find that from anomeric carbon there would be an elimination of OH group. From a non-anomeric position, often there is an elimination of hydrogen. So in other words, there is a removal of water molecule. And the bond which we found would be represented like this. It is like this. Okay. This bond is referred to as O-glycosidic bond. This bond would be referred to as O-glycosidic bond. If on this side, instead of OH, there would have been NH2, or if it is an NH2, obviously hydrogen would be donated from a NH2. Then in center, instead of oxygen, there would be an N. And if it is NH is in the center, then it would be referred to as N-glycosidic bond. Okay. So, but in sugars, from opposite side, there is also OH. So you form a O-glycosidic bond. So the simplest of oligosaccharide could be disaccharide. And in disaccharide, the simplest disaccharide is maltose. So maltose, it has 2 glucose residues linked by alpha 1,4 glycosidic bond. So what happens is that this, let's say this is 1 glucose. Again, you do not have to remember the structure. Let's say this is 1 glucose, this is the second glucose. So let's say this is a second glucose. This is the first carbon, this is second, third, fourth, fifth and sixth. First, second, third, fourth, fifth and sixth. So bonding is in between a first from 1 glucose and fourth from another. Because first carbon is anomeric carbon, so we have to tell whether this first carbon OH group was down the plane or above the plane. In fourth carbon, you doesn't have to put alpha or beta, because fourth carbon OH group would be down the plane, because if it would have been above the plane, then it would not be a glucose, then it would be referred to as galactose. Okay, so from fourth carbon is not an anomeric carbon, so you doesn't have to refer it as alpha or beta. Only when an anomeric carbon is involved, you have to put an alpha or beta. So what you're saying is that now OH group from this side and H from this side is eliminated, and there is a formation of a glycosidic bond, which could be represented like this. O-glycosidic bond is formed like this. CH2OH, this is OH, this is OH. This is like this. So glycosidic bond is between alpha 1 with a 4. Okay, so bond, that's why is referred to as alpha 1,4 bond. Now, although one of the anomeric carbon is involved, in bonding, these are the anomeric carbon. One of the anomeric carbon is involved in bonding, but still one anomeric carbon is free. That's why maltose is referred to as this is the reducing end, and this reducing end is free. One of the reducing end, it is involved in bonding, but another reducing end is free. And if it is free, that's why maltose would be referred to as a reducing sugar. It is referred to as reducing sugar. During the formation of maltose, there is an elimination of water molecule. So molecular weight of glucose is 180. Molecular weight of this is also 180. The molecular weight of maltose would be 2 into 180 minus 18. Why minus 18? Because one water molecule has been eliminated and the molecular weight of water is 18. So you will say that 360 minus 18, it will come out to be 342 Dalton. So molecular weight of maltose is not exactly double of glucose. It is 18 unit lesser because one water molecule is being eliminated. Okay. So similarly, if someone asks you what would the molecular weight of maltotriose, that is, there are 3 glucose which are linked. Maltotriose, what would be its molecular weight? So you can see that how many glycosidic bond has been formed? 2. Number of water molecule which would be eliminated would be equal to glycosidic bonds, because wherever there is a formation of glycosidic bond, there would be elimination of water. So you will say that 3 into 180, that will come out to be 540 minus 2 water molecule have to deduct. So molecular weight will come out to be 504. Why not 3 water molecule? Because only 2 bonds is formed. But if someone tell you that it is a cyclomaltose, if it is a cyclomaltose, what would be its molecular weight? Cyclomaltose means it would be like this. This is cyclomaltose. So in cyclomaltose, you can see that there are 3 sugar, or cyclomaltotriose. If there is a cyclomaltotriose, there are 3 sugars as well as 3 glycosidic bonds. So here you will say that it is 3 into 180, that is 540. 3 into 18, that is minus 54, would be deducted. You will get, okay, almost like this, 486. Okay, so cyclic form, they have the molecular weight 18 units lesser than the linear form, because cyclic forms, they will have one extra glycosidic linkage. Similarly, another disaccharide is lactose. In lactose there are 2 sugars, namely D-galactose linked with, or we can say beta 1,4 linked with a D-glucose. Okay, this is also a reducing sugar. This is also referred to as milk sugar. The maltose could be cleaved by maltase. Similarly, lactose could be cleaved by lactase. So lactase is an enzyme which can convert a lactose into glucose plus galactose. It is present in microbes. Even our intestinal cells, they expresses, but as developmental age or as we aged, the expression of lactase decreases, and that's why often the persons with an old age has a difficulty to digest milk. Okay, phenomenon is referred to as lactose intolerance. Now, if you are interested in structure, you can draw it like this. So this is the structure of beta galactose. This is the structure of beta galactose. Why galactose? Because at 4th position OH group is above the plane. Why beta? Because at anomeric carbon OH group is above the plane. This is our glucose, which may be in alpha or beta orientation. This is first carbon, this is second carbon, this is third carbon, this is fourth carbon, this is fifth, and this is sixth carbon. So you can see here that this is beta 1 is going to form a bond with 4. OH group would be eliminated from one side and H from another side. If it happens, or if you remove OH from this side and H from this side, you can draw the structure somewhat like this. Oxygen would be in the center. The bond which is formed would be referred to as beta 1,4 bond. So it would be beta 1,4 bond, beta 1 forming a bond with a 4. And since you can see that galactose is forming a bond with a glucose, often referred to as beta 1,4 galactosidic bond. If glucose was forming a bond, glucosidic. If galactose is forming a bond, galactosidic bond. Because in molecular biology we study lag Z encode beta galactosidase. Beta galactosidase act on lactose and cleave it to glucose and galactose. But what do you mean by beta galactosidase, which break a beta galactosidic bond? Where beta galactosidic bond is present? So beta 1,4 galactosidic bond is present in a lactose. Okay, because galactose is anomeric carbon of galactose is forming a bond with a D-glucose. It is forming a bond with D-glucose, and anomeric carbon of D-glucose is free, and that's why this is also a reducing sugar. Similarly, my dear friends, there could be a sucrose. Sucrose, also referred to as cane sugar. This is the most common sugar which we utilized. It is the transport form. In phloem of plants. Major transport form in the phloem of plants. Important thing is that this is non-reducing sugar, and that's why this is preferred in plants, because even if it is in higher amount, it is not going to create much problem because it is non-reducing. Here the linkages is between alpha 1 glucose alpha 1 form bonds with a beta 2 of fructose, and since you can see that alpha 1 of glucose and beta 2 of fructose both are involved in glycosidic bond formation, both anomeric positions, they are involved in formation of glycosidic bonds. So that's why this sugar would be non-reducing. If you are interested in structure, we can draw a structure over here. This is, let's say, glucose. So this is glucose, and glucose OH group is down the plane at anomeric carbon. So you will see that it is a alpha 1 of glucose. Okay. And let's say this is the fructose in its stable pyran ring structure. So OH group is above the plane at the second carbon, let's say CH2OH. This is O. This is first carbon, this is second carbon, this is third carbon where OH group would be above the plane. This is fourth carbon, this is the fifth carbon, and again there would be a sixth carbon. Okay. Again, don't worry much about the structure, but this is now the structure of fructose. So this is the anomeric carbon from glucose side, this is anomeric carbon from fructose side, because in ketonic sugars the anomeric carbon or the hemiketal carbon is carbon second. OH group would be eliminated from one side and H would be released from another side. So if it happens, there is a, if OH group from one side and H is released from another side, there is an formation of bond that would be referred to as alpha 1 beta 2 type of bond, alpha 1 beta 2. So since here anomeric carbon from both the sides, they are involved in bonding, it is non-reducing sugar. This is now also non-reducing end, this is also the non-reducing end, no reducing end is free. My dear friends, the optical rotation of sucrose, or you can say the optical rotation of sucrose is also dextrorotatory. The optical rotation of sucrose is plus 66.7 degree. And sucrose could be hydrolyzed into glucose plus fructose by an enzyme referred to as sucrase. It was initially also known as invertase. Why invertase? Because you will obtain D-glucose and D-fructose as a mixture due to action of this enzyme. The optical rotation of glucose would be plus 52 degree. The optical rotation of fructose is approximately minus 92 degree. So the mixture of this if you add this, mixture will show an optical rotation of around minus 40 degrees. So result solution is plus 66, and if you add a invertase enzyme, you find that now the resultant solution which you are going to obtain is a levorotatory. There is an inversion of light. That's why the enzyme has been named as invertase. Okay, because the hydrolyzed product of the sucrose, which is glucose plus fructose, mixture of glucose plus fructose shows an optical rotation of minus 40. Why? Because as compared to dextro rotation power of glucose, there is more levo rotation power of fructose. Okay, so important thing is fructose is major sugar in a phloem. It is a non-reducing sugar. Okay, so these are some of the common disaccharides which you have to keep in mind. So instead of structure, this much you must know that maltose having 2 glucose linked by alpha 1,4, it is a reducing sugar. Lactose has galactose and glucose units linked by beta 1,4, it is a reducing sugar. Yes. Lactulose has a galactose as well as fructose having beta 1,4 linkage. It is a reducing sugar, because obviously whenever one is linking with a 4, it has to be reducing sugar. Cellobiose obtained during the hydrolysis of cellulose as an intermediate have 2 glucose residues having beta 1,4 linkage, again reducing sugar. Yes. Sucrose having glucose fructose alpha 1 from one side, beta from another side, they linked, it is a non-reducing sugar. Trehalose also having a 2 glucose residue, but there is a head-to-head glycosidic bond. Alpha 1 from one glucose and alpha 1 from another glucose, both are interacting together in a trehalose. In disaccharide which is present in, you can say, the hemolymph of insect, it is a non-reducing sugar. So these are some of the important disaccharides. Okay, and you can also take some example of higher oligosaccharides which present in biological system. For example, you can take a case of raffinose. Raffinose is a trisaccharide which is composed of one galactose whose bond alpha 1,6, it forms a bond with a glucose, which form a bond beta 1 with a, or more accurately alpha 1 with a beta 2 of fructose. So there are, in other words, there are 3 sugars, namely galactose, glucose and fructose. And you can see that in this case also the anomeric carbon of galactose is involved in bonding, the anomeric carbon of glucose is involved in bonding, the anomeric carbon of fructose is also involved in bonding. There are 3 sugars, and in all 3 sugars the anomeric carbon is involved in bonding. That's why the sugar is also a non-reducing sugar. So some plants, they transfer a sugar in form of raffinose, which is also a trisaccharide but non-reducing sugar. Similarly, there could be stacchylose and verbascose. Only keep this thing in mind that it is a tetrasaccharide, verbascose is a pentasaccharide. Okay, so if you add a 1 galactose to sucrose, it becomes raffinose. If you add one more galactose by an alpha 1,6 linkage to a raffinose, it becomes a stacchiose. If you add one more galactose by alpha 1,6 linkage to a stacchiose, you get a verbascose. So what is happening is that now one more alpha D galactose, here again more 1 alpha D galactose is being added. Okay, so these raffinose, stacchiose and verbascose, all 3, that is tri, tetra and pentasaccharides, all 3 are non-reducing sugar. All 3 are non-reducing sugar and transport form in phloem where there is symplastic phloem loading. You will study that in plant physiology, that what you mean by symplastic phloem loading. But wherever there is symplastic phloem loading, the transport is form of raffinose, stacchiose and verbascose, while sucrose is transport form where there is apoplastic loading. Okay, so my dear friends, this is about the simple oligosaccharides, that is disaccharides, trisaccharides, tetrasaccharides, and so on. Most of other higher oligosaccharides, they do not occur free in biological system. If there are oligosaccharides, they are attached to a lipids, then it would be referred to as glycolipids, or they are attached to a protein, they would be referred to as glycoprotein. Okay, so with this we compile our today's session. Hopefully you would have enjoyed it. Again, make very short notes. Do not focus much on the structure. You must be well aware what you mean by stereoisomers, enantiomers, diastereomers. At least try to remember the structure of glucose, galactose, and mannose. Then you must know the type of bonding in a sucrose, maltose, etc. So maltose, lactose, sucrose, what kind of bonding is there, whether sugar is reducing or non-reducing. That's it. Okay, so thank you, friends.